I'm going to take probably 20 or 25 minutes and leave time for questions and talk about what we're doing in Chicago, but I want to start with why we're doing it. I and my team have been working with the city of Chicago for about 5 years now, and we've prided ourselves in never going to the city with a solution to an unspecified problem, never coming in with a piece of technology that we're enamored with and saying, here's a really great hammer, help us find a nail. So we started working about 5 years ago with the city on helping them analyze their data. And I, as a computer scientist, found some things out about cities that I didn't know. Primarily in the short story is where you live in a city really affects your experience living in that city. And so we find in all cities, not just Chicago, a huge difference between neighborhoods in life expectancy, or in this case, asthma rates. And if I showed you a map of your town, it would look similar in terms of the distribution of high versus low rates in neighborhoods. We see this similarly with transportation. The gray areas here in this map, it's just a number of minutes to get into the middle of the city from each location around the city. If you're in one of those gray areas, it's a 90-minute trip, maybe longer. If you live in one of the green areas, it's 30 minutes or less. And we don't have data that we need in order to analyze and diagnose how we can address this kind of a issue. Speaking of traffic still, most cities, in fact, I would say I haven't met anyone from any city that has good data about the flow of vehicles and pedestrians around the center of that city. A lot of cities like New York City, unless something's changed in the last few years, and maybe it has, but New York City gets the flow of data from watching the GPS-tracked taxi cabs, not because they know where all the cars are. In Chicago, there's a map of the center of Chicago that tells you red, green, or yellow in terms of the flow of traffic, and we get that from watching the movement of buses as a sort of proxy for the movement of cars. But we don't have good information. In some cases, we don't have information at all about pedestrian flow. You can find a map of pedestrian flow for the Chicago Loop online, and it looks interesting because it's got counts along every street of the number of pedestrians. But in the fine print, you'll see that this was a survey that was done over a couple of days in 2006 with the goal of doing it every 10 years. That doesn't really give you a good sense for pedestrian flow. Chicago is one of many cities that have initiatives in place called Vision Zero, which simply says we want to eliminate traffic-related fatalities by the year 2022. Other cities may have a different time horizon, but in Chicago it's 2022. That's 150 people every year that are killed in traffic accidents, and we want to drive that to zero. But if we don't even have the flow of vehicles, much less, we do have accidents, but much less near misses of accidents, then how can we really implement a safety plan? We can analyze those accidents, and we have data all about them. Were the people wearing protective equipment? Was there speeding involved? Was there drunk driving? Was it an intersection that has lots of accidents? But we don't have any data about near misses, and you can't really have a safety program without that. When we started to think maybe we needed to install some sensors and get data that we didn't have already was when a few of us started looking at predicting crime by not the person like on the movies, but predicting crime on a spatial basis. What you see here is 866 census tracts for the city of Chicago, and a prediction in this snapshot here, 34 hours into the future, with a slider that goes from 1 to 72 hours, and a prediction for each of those census tracts as to the statistical probability of one of three types of crimes. This is viewing violent crimes, but we also look at robberies and assaults. And red just means way more likely to have a crime there at hour 32 from now than the mean across the city, and green means a lot less probability of a crime happening there relative to the mean across the city. We did this partly because we wanted to look at crime prediction algorithms, but partly because we wanted to try to figure out if there's any there to what you will hear from many police officers in cities around the world. The first warm weekend in spring, we get a lot of violence. And you'll hear various stories of weather affecting violence. And in fact, you also can read in the literature air quality affecting people's decisions. So the general environment affects crime and decision making. And we had for this project eight years worth of crime data, every report of a crime of those 3 different types, geolocated down to the street address. But for weather, we only had 6 NOAA stations across the city. So a real mismatch in resolution, and we wanted to try to figure out how to address that. Now, I showed asthma rates in the city of Chicago, and here it's a pretty sad situation with respect to data as well. Now, asthma is affected by air quality, of course, and other things like the age and type of housing that you live in, and you spend most of your time indoors, so that's a big factor. And we have housing stock data in our portal. But these areas here where there's no air quality measurement at all are tens of square miles. And so if I want to compare this map to the asthma map, you'll see that those places that were bright red with asthma, we have no information about air quality. So this got us sort of thinking about what we could do if we worked with the city of Chicago, and by we I mean Argonne National Laboratory and the University of Chicago, to put sensors out throughout the city. And could we do something less sparse than this, using lower cost sensors, but not going all the way down to the lowest cost where you don't have the sensitivity you need to do science, but stopping somewhere in between with emerging and disruptive sensors. Now, the Array of Things project is a platform that we use that was developed at Argonne National Laboratory. And then we got a grant from the National Science Foundation to put 500 of them across the city, which started with translating our tech platform into something that could be mounted on city streets. The first 40 of those locations have been pre-wired already in the map that you see on the right. About a dozen are in as of today. We took a break about 4 or 5 months ago from producing and installing because we wanted to make the jump to third-party manufacturers. We're about to come out of that stage and start putting these out, and there's another 60 locations that are being moving through the finalization process. The rubric that we're using for deploying these is to do specific experiments. You see the stars in the lower west side there. That's about air quality. How often or how closely together do we need to space these sensors, and are the ones we are using going to give us good scientific data? The T shape that goes along the lakefront and then the transect across east-west, those are scientists that want to look at air quality and weather and the lake effect and other experiments you'll see on there. And the idea behind the Array of Things is not to have this special proprietary portal that someone in the city of Chicago can look at and make decisions, but to have data as a public utility and to publish this data. And what we're set up to do right now, it's a variable that we can set, but every 30 seconds, all of our devices are reporting all of their sensor data to a central location, and then we publish that, we'll publish that data once we're up and running in a way that the general public can make use of it, as well as scientists can make use of it, and with APIs so that people can write applications that they might want to. For example, we have 2 or 3 groups that are writing applications that they want to guide you through the city based on air quality. I want to plan my running or biking route, and we'll look at air quality around the city for now in the last 15 or 20 minutes or however I want to do that. So we've got that all set up. As soon as we start to publish, we'll have the way for scientists and the general public to use the data. Now, I've been saying lately that Array of Things is not a sensor network. And by that I mean it's not primarily a sensor network. Your car has lots of sensors in it, and those sensors give data to your car, but your car is not a sensor network. It just happens to need sensors to do its job. Our project is an embedded systems network, and it turns out, as I'll say in a moment, that there are different ways that we are implementing this instrument, if you will, so that different science communities can use it. I should also say Array of Things, if you wonder why we came up with that term. It was a juxtaposition of Internet of Things and the concept of an array telescope, where you have lots of many identical instruments that are pointed at the sky, and together they give you a much better picture of what's happening up in the sky. We're just pointing it down at the city and making it into a public utility. As we went around and did workshops over the course of 2 years or so, talking to different science groups, it became clear that one of the things that scientists want to do is measure things about cities like near-miss accidents for which you can't buy a sensor. And so we go back 50 years to the social science work of people like William White, observing the public way with a clipboard or a video camera like this. And we started asking social scientists, if you could station a graduate student in this park or on this corner 24 hours a day with a clipboard, what would they be observing? And could we translate that into a machine learning capability with images and sound and other data that we could then parse or extract information from images like this one? By the way, this is a stylized image of one of the camera views of an intersection, just to give you an idea of what we're seeing. Our privacy policy prevents us from publishing any of those images, and I'll get into a little bit of detail on how we do that in a moment. And this afternoon, Brett Goldstein and I are going to be talking about some of the policy and privacy implications of projects like this. So I say we're not a sensor network. If we were a sensor network, we would be done already. Sensor networks are really easy. If you have a high school kid that's interested in technology and you give them the tools, they'll figure out how to do a sensor network if they want to within a couple of weekends. It's a board that has a simple processor on it, gets programmed once and put out in the field. It's very rugged. It's connected to a modem that's also rugged, and it sends data up to a cloud. The moment we decided to do machine learning inside the box, our job got way harder, because Linux devices, and we chose that because that's the environment that the machine learning community is using, and we didn't want them to have to do a different set of development to use our instrument. We wanted them to take their research and slap it right onto the instrument without any sort of porting or anything like that. So once we decided to put that out there, we now have a very unreliable, relative to the kind of reliability you want, very unreliable platform, and we need to do some things to make it reliable, to keep these Linux devices so that they're actually running and healthy, and even recover from some known failure modes and prevent other known failures. So to do that, we had to design a supervisor board that takes the hardness and reliability of that simple sensor board embedded in this $4 processor and adds to it sensors that tell how the environment is inside the box where those Linux devices are doing, that can tell the Linux devices to boot from this memory device or this one if there's some kind of a problem, that can reboot them, that can sense that they're drawing lots of current, and so there must be something wrong, and so we're going to have to reboot it. A heartbeat monitor that tells the little rugged processor whether those things are running or not. And we had to build lots of software into this, so in fact we now have a system where these three computers, if you will, can keep each other healthy. If we decide that we need to upgrade the firmware on that supervisor board, those Linux devices can do that. And if it experiences a power failure during the middle of that, like you're told when you upgrade your firmware, don't unplug it, well, we've got some logic in there that can protect us from that. So we built a very reliable system, and the simple reason for that is maybe two reasons. One, it's expensive to put stuff up in cities. Relative to the cost of this box, the labor for a crew of 3 electricians to go out with their bucket truck and wire things up, that's an expensive thing to do, and you don't want to waste their time by sending them out to fix things. It's way up on a pole, so we can't go out and hit a reset button. And the second reason for reliability is we are going to put 500 of these across the city, and if 10% of them fail every year, that's 50 times that a bucket truck crew goes out and replaces something, which adds up. So we did all this, and now we've got this fairly complicated system that has a sensor board that we designed in the upper left, one that's printed electrochemical new experimental gas sensors in the upper right, with a board that we partnered with Intel to design. The light sensor board, we have a camera that's pointed straight up at the sky that gives us general light. It gives us 5 megapixel images of the sky. It gives us infrared and ultraviolet as well, so we can use that data to look at things like solar loading on buildings. We have all this stuff. You can see one of the Linux processors that's there on top of the supervisor board, and we got to put it all together, which tends to be fairly complicated with these devices. So we've gone through initial engineering phase. Our next stop in the next few months is to streamline the internal design. This is just the assembly instructions for, I think I need to add the little IKEA man to this diagram, for what we call the brains, which is the thing with the umbilical cord on the left-hand side. That's the supervisor board sandwiched between a couple of those two single board computers. I have no intellectual comment or content on this slide here, but it's sort of fun to see the assembly, and you can see on the right-hand side there the green brains, and if our sound guys can click in the right place, we can see an animation of the assembly of this device. We've had to speed it up just for interest of time, so actually the installation or the assembly of this elapsed time is probably about 2 hours, and this is a person that knows how to do it. We've learned in this project that hardware is tougher to do than software, and assembly, and for one reason, you can recompile a software program in a few seconds, but if you want to recompile, if you will, a hardware board, it's more like 9 weeks turnaround. Assembly is also the more complicated device, and ours is fairly complicated, the more expensive it is to assemble. So we're in the handoff to the third-party manufacturer, we've had to write tests that our folks wouldn't have needed, put harnesses in place so they can test subcomponents before putting them together and give them the sort of instructions that you would expect to get if you walked in off the street and never seen this thing before. That's not what we're used to doing in a laboratory or university. Now, when we wanted to put these up in the city, the native device called Waggle, the native platform that I've just been describing from Argonne, didn't look like this picture. We had to package this not just for aesthetic reasons, but functional reasons. The blue boxes got a couple of waterproof boxes in the back. At the top, you can see in the bottom left corner the brains inside the aluminum waterproof container. And that's at the top of the Array of Things blue section. The bottom is a plastic box that has an AC-DC connector, and we separate AC and DC components for safety reasons and simplicity. You can then see, second to the left on the bottom, the sensor harness that hangs inside the white stack of domes. That's a shield that protects the devices from direct precipitation and direct sunlight. At the top of that dome is an AT&T modem that connects us with cell phone network. We've done Wi-Fi and direct wired, and we're working on mesh networking as well. But to simplify our lives, we just partnered with AT&T and let them worry about the network. So there's aesthetics involved, but also if you think about the cost of installation, we do want to upgrade these over time. And that means we wanted the installation to be done, and then very quickly we wanted to be able to replace the devices. As we worked with the Chicago Department of Transportation, who are doing the labor for installing these, our goal was, we said, we want you to help us design the mounting and the packaging so that it takes you no more time to replace an Array of Things node than it would take you to replace a holiday decoration. A guy goes up, or a gal goes up in a bucket truck, and this should take about 10 minutes to replace. Like everything else on poles, and you can see it there as well with that ominous black thing, whatever that is below ours. It's just a standard stainless steel strap that goes around the pole, and then you can see the yellow loop of wire underneath ours. It's a standard screw-in waterproof AC connector. So I've already talked about resilience. Of course, the simplification of installation gives us, I've said to people also, you know, at the end of the next 2 or 3 years when we have 500 of these across the city, the most exciting thing about that will be 500 yellow wires like that with power, so that we could put anything up on those poles that would follow on this. So it gives us an opportunity, if it's cheap and quick to replace, to do an ongoing set of experiments and upgrades. Now, the way all of this works together, you have a bunch of nodes out there, they're talking over a cellular network, they're sending their data back. Most of the scientists we talked to were very interested in measurements and not so interested in the technology. And so of all of the scientists we worked with, it was the scientists that just wanted measurements that we started with, a sensor network. And you have to keep various versions of the data, because later we may come back and say maybe the calibration was off and we want to correct for that. But basically those 3 values for every measurement we need to keep over time in a way that people can reference. So I write a paper that talks about transportation and air quality, I need to be able to reference the exact data that I used, and the raw sensor data is just the electrical signal coming off the sensor, a voltage or a current level typically. The measurements, if you will, after that transformation are the parts per billion or the degrees Celsius, what that voltage level or amp level reads. And then in some cases, the sensors have a different response characteristic based on things like temperature or humidity, or they may have an offset that we find in calibration. And so in some cases, we have to also have corrected data. And it's in that final step that we want to make sure we keep the previous data, because we might be wrong about that and discover later that we can get better data by reapplying a different calibration function. These devices are intended to be very secure, and we've done, I think, a pretty good job of designing an architecture that's secure. They run with no open ports, so there's no way for us to connect to them. They've got to connect to us. And they connect every 30 seconds and dump their data, and then they check to say, do I need to upgrade my software? Do I need to open up a reverse tunnel to the techs at Argonne so they can log into me? All of the code is digitally signed, all the communications are encrypted. So we've tried to make this a very secure device and do both this management and data over the cellular network. I should also say, every 30 seconds, it's only a few thousand bytes of data, because we're not sending images or sound. We're doing the processing of those inside the box, and then they get deleted. We've had, I think I have a map later. I think we've now exceeded 80 different cities and universities that have said, we'd like to buy a couple of those. When can you sell them to us? And we decided, for our own survival, along with some other probably better reasons, but certainly for our own survival, we would offer a turnkey installation and cover all of the communication. And all you have to do, and there's one in Denver, there's one in Seattle, is put it up on a pole, strap it in, put power in, and then it does the rest. It connects back to us, tells us where it is based on GPS, and starts to send data. And then, just like the city of Chicago that doesn't have internal hooks to get into the data, they get the data through APIs to a system called Planario that I'll show you in a moment. They can look at streams of data from a commercial system, or they can go in to data.cityofchicago.org, which is our Socrata open data portal for the city. So I mentioned the aesthetics issue and making sure that it was quick release and quick mounting. As I also mentioned, Brett and I will talk about policy and privacy this afternoon, but it's a common question: how do you decide where to put these? We have scientific reason for deciding on these locations, but what we wanted to do with this device, and one of the reasons why it's not black and ominous but is more conspicuous and colorful, is we wanted people in neighborhoods who had this device to think of it as their device that's watching the city on their behalf and giving them data about their neighborhood. And so when we go in with any of these experiments, or as we expand out from this 40 to 500 across the city, we're looking for three things that need to be true of a location in order for us to say, yes, let's do it. And the very first one of those is, are there residents or businesses there that have an interest in a particular challenge or issue or problem? Could be air quality, could be noise, could be traffic safety, but we need to start with something that the people who are going to host us in their neighborhood actually care about. And the next question is, are there scientists out there that if we gave them data about that particular, let's say it's traffic safety, that they could give us some insight from that data, the residents in the city? And then the third requirement is that somebody in the city of Chicago actually cares about that insight and that data. So none of these are technical reasons. The technical reasons are really easy, and it turns out that Chicago is large enough, with 600 square kilometers, that 500 nodes, if we find a neighborhood that really doesn't want these things, then that's okay. We'll move to another neighborhood where the people would like to see it in their neighborhood. So far, we haven't had anyone tell us they don't want it. We have learned in our many interactions with the general public that people are generally okay with surveillance of their neighbors, but not of themselves. So we've been asked to surveil neighbors, but told not to surveil, don't surveil me. I mentioned Planario. There's ways to interact with data through the City of Chicago data portal, but we wanted to build a tool that would allow data discovery and examination, not the hardcore analysis, but of data across many different portals. So Brett and Goldstein and I and others came up with this idea that we borrowed from WindyGrid in Chicago, which is let's give scientists and policymakers a map and a calendar and say, just draw on the map the place that you're interested in, the period of time you're interested in, and we'll tell you what data is available and give you some indication off on the right of the temporal signal of that data. Maybe it doesn't have, as you see at the top, data, but part of the period is covered, and maybe it's covering the whole thing. And maybe I'm interested in food safety, and so I've selected here the food safety inspections. And so now I can get a spatial signal. And I can zoom in on that. The first one was at 500-meter resolution and the density there. And I've zoomed in and said I want to have 100-meter resolution. But I only want to look at, because I've got the structure of the data in the system, it's a geospatial database, I know what the fields are. So I said, I want to just look at the inspections that were triggered by a complaint. And now I've got that filter running, and I can zoom in now on just those inspections where it was based on a complaint. I could do the same thing with crime. I could only look for armed robbery. Not that that happens in Chicago. I can only look at abandoned vehicles or what have you. So once I then do this filtering, I say, yes, this would be useful data to me. I can download it in various formats and then go off and do my thing. Now, when we started the Array of Things project, we added to this the capability to ingest sensor data, to organize it in a way that would be useful, and then to have APIs so that people could write applications. So once we start to publish the data, we have not only Planario, which I was just showing you, but OpenGrid from the city of Chicago that connects in the front of our geospatial database using the same APIs as I just showed you, but now has an interface that's really tuned toward residents rather than scientists. My yellow light's turning on, so I'm hoping to finish in time to at least take a question or two. We've been interacting with artists like this group here that's got a lighted bridge along one of the major running trails in Chicago, and they want to make those lights indicate in some fashion air quality. They're indicating temperature now. We are in the second year of teaching an 8-week curriculum at Lane Tech High School. Last year, 150 kids. This year, 160 kids. That started with, I want to ask a question about my school. Selected a sensor, built a sensor node, packaged it with their makerspace, put it up in the school, gathered data, and analyzed that data in teams of 3. And this year, as we go through this, we're packaging this curriculum so we can do a workshop with high school teachers and hand them as much curriculum as we have and help them get started on similar things. Maybe I'll close by referencing back what I said before about this 80-plus places that want to try out the Array of Things. We're prioritizing that map there based on, if you remember, I said residents, scientists, and city need to be interested. We can't make a judgment call about whether a neighborhood in Stockholm is interested or not, but we can make sure that there's a team in place between a university or national laboratory and the city. And so the red ones there, that team's in place. The yellow ones are going to stay yellow until we're assured that we're not just throwing technology at a city or university, but we're actually meeting a need that they've defined to diagnose some aspect of their city. Now I have 1 minute and 35 seconds, so I'm happy to take a question, and I'm be happy to stay around to answer more offline as well.
How would a scientist cite data that they got from your program in a scholarly article?
This is a question we're going to have to try to figure out because it's not very common. All of these data sets will have digital object identifiers, so we'll be able to cite a DOI. And I'm not familiar enough with citation processes as to whether that's a common thing or not, but we want to make sure that the data set you use for your paper, you can go all the way back to it, even if later we change the calibration and the data might be, there's a new version of the data. We're down to 43 seconds. Yes, in the back. Hold on. Here we go.
So I understand you're tracking like weather and street activity. Is there like a roadmap for other type of data beyond that once you have collected those 3 types?
So I didn't say what all we're sensing. There's about 16 or 18 sensors in there, 7 different gases, particles of various sizes, temperature, humidity, vibration, barometric pressure, magnetic field. It's a bunch of sensors we're collecting data from. For the image and sound processing, we're working with different communities that do machine learning to extract information from sound and video, or in this case, we're doing still images. And as we add a capability that says, let's say we're going to count pedestrians, then we'll publish, we're counting pedestrians, and here's a link to the data that counts pedestrians. And over time, that will be a longer and longer list of things that we're examining. The city of Portland has asked us to work with them as an example to use the image processing to determine as a bike goes by, is it a private bike or a bright red Portland bike share bike? And secondly, is the person wearing a helmet? Because they have this theory that their bike share program is encouraging people to ride without helmets, but they don't have any data about it. So when we get that classifier in there that does that, it'll be published on the website. This is what we're collecting, and here's a link to the data that's out there in the portal. So I'm out of time. Thank you so much for coming and hearing about the project. We'll be back this afternoon to talk about policy and privacy and other fun things. And I'll stay around if anyone has any offline questions. Thank you very much.
Thank you so much.